Today we are going to discuss about process, its creation, termination, and how it is being handled by your operating system. So quickly going over, the early computers allowed only one program, and which is now not a case even for a single device, even it is for embedded systems. So there are multiple programs or processes are running. So a program under execution is called a process. There are multiple processes, those are running onto your system, so there need a better control of the mechanism by which we can control multiple processes. And this process is unit of work in modern computing. And nowadays we have threads also, so process can create multiple threads. So thread become your unit of work, but that is already like always initiated by a process. So a process can create multiple threads, so that give rise to the concept of multi-threading. Okay, so basically the batches and jobs are basically the earlier term that is used, but still when we talk about different Hadoop system or multiprocessor system where we have network computers, we call them jobs still. And there are job schedulers, those basically switch the job. So now to the finer grain, with the evolution of the computing, we call that as a process. So process is a program under execution. And a process, when it is loaded to the memory, so we know that loader basically loads a program into the memory. So when it is loaded into the memory, let us suppose main is a program, it is basically allocated some address space. When we say about address space, so there are certain sections of that particular process that has to be given addresses from the memory. So there are multiple sections of a program or a process, one which include the text section, the other which includes basically the stack, then we have data section, and then we have heap. So there are four sections for each of the process. Text section just hold the instruction set, the program code, whereas your data section holds the data which are represented as a global variables. Then we have stack and heap, those are basically um, uh, increasing or decreasing locations where your process, as you are executing or running your process, it will increase and decrease the size of the stack and the heap. Now the most important part is what is actually kept in stack and what is in the heap. Stack basically saves the function parameter, return address, and the local variable. So everything that is defined in your program as a variable at the start is goes into stack, and anything that is dynamically allocated would go into the heap section. So if I say, let's suppose I create a class like this method. So when this is basically called, when your program would be running, so what part would go to stack and what would go to the heap? Basically this part would go to stack, and this part which is dynamically created, it would go to heap. So both are memory locations and holding the variables and their values, but there is a fine line between these two, that what would be stack would be holding and what heap would be holding. So these are dynamically changing things. So whenever you call a function, and location is would be created onto your function. So let me show you what exactly is your the sections for the process looks like. So there is a text section which holds the code, then global data, and this is a memory location for dynamically allocated variables. or location. Then this includes local variable and function calls. So everything will be put onto stack. So you know that this mechanism is used in your uh, ADT. You worked on ADT during your CP164, so you know what stack and how it works basically, and you also know about heap. So both are given the this memory location, and both are using the same space. They are increasing and decreasing. So whenever a function returns from its work, it would be removed from the stack. And whenever a variable we have given allocated some memory, it has finished its task, we can deallocate and it will actually remove it from the heap. So both these two sections are basically variable, whereas data and text are fixed kind of memory locations. The size of the text and data section are fixed and does not change. However, stack and heap section shrinks and grow during the program execution. And there is, whenever a function is called, activation record is containing the function parameter is pushed onto the stack. Program is your passive entity, and whereas process is your active entity. Whenever it is loaded, it would be allowed or allocated the address space. So a single process can have a program can have multiple processes. So you can run the same instance of a program multiple time, and they would be working as an independent process. Consider the multiple user executing the same program, or there are multiple windows for the same program. You open your browser multiple times, those become independent processes. Each of these may be a separate, although the text sections are equivalent. Data, heap, and stack section may vary. So there is some sharing between the processes which would happen. Uh, like your Ubuntu, if you want to look at what would be allocated to this particular executable file when it is loaded, so the size would be of this many. This would be the size, and then we have data section is basically 560 here. So basically this whole data set is in bytes. So what the number of bytes for text section, then we have number of bytes for data section. BSS is used for holding the initialized data, and then we have uninitialized data too. Then this is a decimal representation and hex representation of the total number of bytes that are used here, and this would be representing a file name. So if you want to see that what would be the size of your program and how it would be allocated, so this particular command would tell you like what would be the initial state of your process. Okay, so data field is basically referring to uninitialized data, whereas BSS refers to the initialized data. And these two values are some of the three sections represented in decimal and hexadecimal representation. Now we know that just to recap, you create a program, you compile that program, and then load that program into the memory. When it is loaded, it would be given provided as an address space. And when you load this program, a new process would be created using fork, and it's basically data would be loaded. So this would be automatically called here. Now, once your process is in the memory, it will wait for to be sent into the ready queue. Now, there are different states for each and every process. These states could vary based on operating system to operating system. So the basic are new, running, waiting, ready, and terminated. New when the process is being created, running when the instructions are being executed on CPU, waiting, the process is waiting for some event to occur. So IO or resource allocation is there. Ready when the process is waiting to be assigned to the processor, and terminated when the processor has finished execution. So these 4 5 instruction the states are there. So each process would go through all these states whenever it is under execution. Now this diagram shows the different states and how your process goes from one state to another state. So whenever you created this is step number one. Then it goes to a ready queue. So using a long-term scheduler, it is basically selected from memory and put onto the ready queue. And when it is a ready queue, it is waiting for running. So there would be a CPU scheduler that takes the input from the ready queue and put onto the running condition. So when the process is under running condition, and then it is basically being executed. Now, can you tell me like how many processes could run concurrently under this state? What would be the number of processes which would be running on CPU? What decides this? Okay, so who decides it? So if we have one CPU with one core, how many processes would be running at same time? One. Yes. So if we have two cores, how many processes can run at same time? So it depends upon number of cores basically. So in multi-core, we have multi-processes. So basically not a process, it would be thread. So if I say one core, it will be one process with one thread. It may be one process with two thread, one process with multiple threads. So we talk about that moving forward, but right now just make it as a process. So one process at one time would be running on your CPU with single core. So either your process would be running now, it finishes to get completed and exit and get terminated, and otherwise it may be waiting for some IO event to happen. So if it is waiting for IO event to happen, it goes to the wait state. So this is a wait state where your process is waiting for some event to happen or IO to respond. So as we know that the whole idea of operating system is number one, CPU utilization, number two, best response to the user. So for that, your operating system performs the context switching. So whenever a process is waiting, your CPU would actually switch to a different process and put the current running process into the wait state. So whenever this wait state is over, so from here, it goes here. So whenever it is basically the wait state is over, your process would go into ready state. And there are other mechanisms, like three things could be happening when a process is under execution. Number one is wait state. Number two, that is it is interrupted by interrupt. Number six is it's terminated. So whenever it happens, like step 4 or 5 happens, the next state of your process would be ready state. So this is how basically your process goes through different states while it is loaded into the memory and goes for execution. So basically, there are like I like this state there, as I told you that it depends upon different mechanisms. So Zybook has a different state diagram. One we discussed with, which is given by Galvin book, and now here you can see like how your process would run. So it basically starts with a new thread. The OS moves the process from new to the ready when the process is allowed to compete for the CPU. So this is also selection, like when a process is to be moved to ready queue. This is also done by a scheduler. So when you load your program, then it has to go to the ready queue, and there it will compete for which one should be sent to the ready queue. And transaction, this is called activation. Now in second stage, from the ready queue, the process can move repeatedly between running, blocked, and ready. So before it is basically terminating. So from ready, it can go to running, and from running it can go to block. Now block is wait state here, which is equivalent to wait state what we have discussed. So whenever a process goes for running, it goes into block state if it is requesting for some IO or something to be happened. Now, okay, so in addition, OS can move the process from running, ready, or blocked state to suspend state to temporarily prevent the process from making any progress. So this is another state which is added. Likewise, I said it depends upon operating system to operating system. The most basic states are given by Galvin book. Now these suspended states are added to upgraded operating systems, which basically suspend the your process where OS wants to stop a process to allow debugging or to regulate the performance. So a process may be placed to suspend even though CPU and all its sources are available. So it is up to the operating system if it wants to suspend some particular process for some time. So whenever it is suspended, it can go back, reactivate, and it will go back to the same state where it was suspended. So if it was suspended in a blocked state, it will go back to the blocked state. If it was suspended from the ready queue, then it will go back to the ready queue. And after this whole process completes, your work would be, or the process would be terminated, and it will throw an exit command. Okay. I hope this is a bit clear. Like each process goes through different process states. Now, the most important part or the fundamental part of a process is process control block. Before that, I just want to show you the status of your process. Let's go to the directory proc. As I have told you that it contains every information that is needed by you to view the state of the processes. So here you could find all these are the processes with numbered, because in Linux, all processes are numbered. In addition to it, there is some other information that your proc folder holds. So basically, if you want to see the CPU info, it'll throw every part of this. So most of the information that you need for your operating system or your system, that you can get it from here also. Like if I have to say, okay, I want to see into the process 1406, I can go into this directory and I can see it may need sudo power. Then you can see all the information which is available here. Now, if we want to see the number of threads those are running, then you can basically go into task. So here you will see that it is just a single thread process which is running right now. And if you want to see the status, you can see that by stat. Sorry. So it will actually show you what is the state of this process. So this process is currently sleeping. So likewise, we can get hold of the information that we want about a process from proc folder. Okay, now moving forward, here is the process control block. So whenever we say a process, it would have, other than a current running state of the program, like other than the data, the task, there are many things those are associated with it. So we were talking about, like, we perform your operating system perform context switching. So when a process it has to perform context switching, the whole state of the process should be saved into a file, that is process control block. And process control blocks not only hold the memory information of the process, but also the running state, the program counter, the CPU register. So what was the state of the CPU registers when it was running? So there are many registers on hardware, accumulator, index. So there are flags. So all those in CPU register has to be saved somewhere. So process control block is that block which is used to carry information for each and every process. So program counter basically counts a location of the it always hold the location of the next instruction to be executed, very important. CPU register, then CPU scheduling information such as priorities, scheduling queue pointers. Then we have memory management information that the memory is allocated to the process, that includes a memory limit and other stuff. Then we have accounting information, how much CPU is used, clock speed elapsed since start, time limits, and other timer information. Then we have status of IO, that includes the IO devices allocated to the process, lists of open files. So all that is basically handled or saved into your PCB. So there is one very good animation. So when your process is created, so how does it go? Let's suppose you're trying to log in into a system. So before user logs in, only OS processes are running. Each process is represented by a PCB. So for this, a PCB knows that the program and the resources, which points to program and resources controlled by the process. So PCB holds all of the information about your process, and the horizontal arrows represent the program counter. So this is how it will be actually executing. Now, whenever user one logs in, a new PCB is created. So for user one, a new PCB would be created, which typically execute the graphical user interface and to the initial resources those are needed. Program counter points to the start of the program. So basically this would say, okay, what is the first instruction to be executed? So whenever a loader loads, it also provides the start or entry point to that program, which is the first instruction, which is normally to be executed by the process. So user is running. The screen shows the icon of different applications. So there are different applications those are running. And when user clicks Microsoft Edge icon, a new PCB would be created by an OS. Now, one process was that the user login. Another process was now when somebody starts an Edge, Microsoft Edge. So there are number of processes, those are running currently on your system. So you can always see that PS is basically giving you the number of processes those are running. So I can do that, like I can count the number of lines. So you can see there are right now 95 processes which are running on your computer or Ubuntu machine. Now we have discussed about program, how it is loaded into the memory, what are different states of it, and now something about context switching. So you know that a process inside operating system is represented by its PCB. So PCB holds every information about execution, status, and all other memory locations, list of files, CPU positions, so everything is there. So basically, whenever we have operating system has to perform context switching, it save the state to the PCB. So, and then whenever it has to reload the process, it fetches the information from the PCB. So here is how it performs the context switching. Let us suppose your process 0 is executing. This when this process is executing, so you want uh, is there is an interrupt that has occurred. Now, interrupt could occur in multiple ways. It could be either hardware interrupt or a software trap. So based on that, your CPU would actually start saving the state of your process 0. So where it would save the state of your process, it would do it on PCB 0, which is handling the information of the process 0. So once it saves the state, it tried to reload a different process. So it will try to load PC state from PCB1. So PCB1 holds the state information of process 1. So whenever a trap occurs, so the process is the CPU saves, your operating system saves PCB0, then reload the state from PCB1 and start CPU start execution. So blue line is basically telling that CPU is executing one process. So here, for here to here, process 0 was running. Now here to here, your CPU is free. Here to here, it started executing P1, and again there is an interrupt, so it saved the state of PCB1 and then reload the state of PCB. So from this part till this part, it is idle, and here onward it started executing process 0. So certainly when we perform context switching, there is an overhead that your CPU is idle. Because we want our CPU to be 100% utilized, there needs to be faster switching of um, your processes. Okay, so switching from CPU code to another process require performing state save and the current process and state restored from a different process. This task is called context switching. Yeah, somebody's mic is on. Okay. Okay, moving towards threads, that is our next chapter. So basically each process can initiate number of threads. So those threads would be the smallest unit that would be a processor would be executing, and threads are allocated to different to the CPU. So this thread comes up with the multi-core processing. So because one process can create multiple threads and they could run in concurrent way or in parallel if you have multiple cores, but always there would be some dependency graph that the dependency of T1 over T2 and T3 that would also be managed by the dependency graph when multiple threads are running. Anyway, so for a process has a single thread of execution, so one process with one thread we have seen. There would be one process with multiple threads. So let us suppose 10 threads are initiated. Now, in a process, for example, if I take example of JVM, Java Virtual Machine, you can see this is one process, and within this process, you can execute multiple programs. Those would work as your threads. Or if I say your Docker is one program, one process, and within Docker, we can run different machines, and those can perform different tasks out of it. So one process can initiate multiple other processes also. So how many of you are familiar with Docker container? Okay, okay. So uh, if if you want that, you can read about Dockers. This is a new type of virtualization, not something which is more advanced like virtual boxes, but this is better when you want light machine. So Docker is a container basically. It perform the virtualization at OS level, whereas your virtual boxes perform virtualization at hardware level, because VirtualBox isolate your host operating system from the guest operating system, whereas Docker runs your machines onto the same operating system, but provides the required uh, space for a process to run and hide that particular space. So if you want, you can run Ubuntu machine onto Docker. Like all those who are programming and preparing their self for cloud application or next step, then basically those are working on Dockers or Kubernetes. So basically, these are two technologies that you should actually learn about. Virtualization is one you are already doing. So boxes you are using. So those would create your virtual machines and you can run anything. So basically that's separating your two operating systems entirely, whereas your Docker provides the OS level virtualization. I mean to say, you will enter into your Mac operating system, and on to Mac operating system you start Docker, and then you can run different images. Those would be isolated at Docker level. Anyways, those are a few concepts which are beyond the scope of this course, but just because this is related to something virtualization and operating system as services and processes, so that's why I discussed it. Okay, so one process can initiate one thread. It can create multiple threads. So for controlling the multiple threads, we need TCB. So each process would have a thread control block, which would actually holding the information of each and every thread. So this particular threads we will be discussing in the next chapter. But for your example, like if you open Word document, then if it is a single threaded process, you would not be able to simultaneously entering into your program and also doing the spell check. If you see that your word processor along with while you are typing also checks for the spell, that happens because it creates two threads for the process. One which takes care about the data being inputted, and other would just check for the spells what is being inputted. So that basically separates and create two threads. So one process is split into two threads. So that's multi-threading. Now here we have a process representation in C. So you can always look at this is a struct type that is used for the PCB. It holds the basic information about the process. So the process identifier, then its state, then the time slice, which is the scheduling information, the process parent information, children information, then the file those are open, and then the address space for this particular process. So basically your operating system or Linux uh, handles these processes in a doubly linked list form, where each structure would be basically a linked list form and would be of this shape, where your operating system manages one pointer. That pointer points to the block which is currently running and executing. So using this particular pointer, you can actually change the state and status or other values within that structure. So it's very similar to what you have done in CP164 linked lists. So everything mostly in your operating system, the data structure beneath is linked list based data structure. So okay, so I have to show you this whole information is basically located at under. You can locate this is a file which basically explains this structure, whole structure. You can always locate, you can use locate file, and then you can look at this is a file include Linux schedule. So this is the file which holds this structure task struct of the process. This is defined here inside this particular header file. You can have a look at it. Now going to the process scheduling. So why why scheduling is needed, because there are multiple processes those are running, and those are available for to be executed. So the number of processes those are currently in the memory are is showing the degree of multi-programming. So how many programs or how many processes your operating system or your computer can actually process, that becomes a degree of multi-programming. And CPU maximizes its utilization by switching into multiple processes, and we need some scheduling mechanism by which we actually allocate the processes to the CPU. So CPU is just executing, it does not know which process it has to execute next. So we need to create some either priority queues or queues which are basically used by your operating system to execute to perform the execution of that process. Now this is clear to you everyone that each process when enter into the memory, it would be started represented as a PCB. So PCB takes the control of everything whatever is related to your process, and then this PCB is allocated to different scheduling parts so that different scheduling algorithms or the queues can be implemented, and this could be given to the CPU. Not too complex much, so there are basically process scheduler selects among available processes for next execution on the CPU. So all processes which are in the memory, they try and wait for the CPU to be for its execution. Now there are two types of processes. One are inbound IO bound processes, some are CPU bound processes. So inbound processes, those spend more time on input output. They run for nanoseconds or milliseconds, and then they go for wait state, just waiting for IO to happen. And there are CPU bound processes which are like more compute intensive without waiting for any data from input from the user. They just keep on running on your computer. So those are CPU bound processes. But you remember that your operating system are multitasking, so there is time sharing concept. So each process would be allocated to CPU for a limited time of when it will execute. Uh, I think we haven't discussed about real-time operating systems much. So real-time operating systems. So real-time operating systems are one where there are different kind of priorities and deadlines associated with each and every task. So in that case, the deadline would be deciding factor which task would actually execute first. Let us take an example of automatic braking system. So in automatic braking system, let's suppose Tesla. So if an object is in front of the car, your processor is running the tasks which are more related to other environment of your car. But whenever it sees that there is a car in front of it, then that task would become, or that process would become highly critical. And in that case, it will preempt all the processes which are currently running on CPU and run that particular task or job or process. So it depends upon like how the scheduling mechanism is done. It depends upon the operating system. It depends upon the task. So there are priorities associated with it. I remember you know priority queues, how the priority queues are generated. So priority queues are generated based on the priority. The priority parameter may be the deadline. It may be the severity of the task. So based on that, each scheduling queue would be prepared and allocated to the CPU. Now, it may be possible that some tasks may be exempted from time sharing. They would always, whenever they run, they would always complete. Some tasks may be there which can be preempted, like which can be stopped by an interrupt, and the CPU can be allocated to other processes. So scheduling queue, there are different queues, a job queue, then we have ready queue, then we have device queue, then the processes are migrated from these various queues. So process would go from one scheduling queue to another scheduling queue. Let us see the ready queue. Ready queue is again a linked list the queue holds head and tail of that particular queue. So you can see the process PCB7, and then we have at here PCB2. So this queue is used to allocate the task for execution. So this is ready queue, then we have wait queue, then we have different devices and they could have their own queue, and each process is basically there are multiple processes waiting for the device and their control. So there are queues for each and every device. Now this represents the simplified diagram of how the process would be going. So CPU is basically running these from ready queue. Then either the CPU would actually shift it into different states. So if there is an IO state, IO request, then it will go to the IO queue. If it is a time sliced expiry, like the time given allocated to a task is over, then it will actually switch. The CPU would perform the context switching and your process would go into the ready queue. If there is a fork of child, like this process would create another child. So your parent process would wait for the child to execute and to complete. So child would execute and then once it basically done, it will again go to the ready queue. Or whenever there is an interrupt, that interrupt would be handled, and after the interrupt is handled, so it would again go to the ready queue. So this is how the life cycle of a process which would be there. So whenever a process is initially put into ready queue, it waits there until it is selection for the execution or dispatching. So this we have discussed. Now there are three types of schedulers. One is called short-term scheduler. We will discuss in next coming lectures about CPU scheduling. So select which process should be executed next and allocated to CPU. So this is called short-term scheduler, whereas a long-term scheduler is called job scheduler, which selects which process should be brought into ready queue from the memory to the ready queue. So this is selected by long-term scheduler, and the CPU scheduler is selecting the process from ready queue to allocate it to the CPU. Now, there is another medium-term scheduler that can be provided by your operating system by the concept of swapping. What it does is, if your memory RAM size is small, it can actually swap some of the processes from main memory and put back onto the disk. And whenever it requires, it can pull back the processes from the disk. So basically, this reduces the multi-programming, but also helps to manage the memory efficiently so that there is no memory overflow. So it removes the process from memory and store onto the disk, bring back from the disk to continue the execution, and this process is called swapping. Swapping is typically necessary when memory has been overcommitted or must be free. So this feature is used when we have to look for the memory management. So this is called a medium term scheduler. Now talking about mobile operating systems. So as we know that different processes are running. iOS initially just allowed one process to run, and nowadays we can actually run multiple processes. Some would be running at background, and it also provide the functionality to run two programs at same time for foreground. Those are active processes using split screen. So split screen provide us the interface for two programs at same time. So that functionality has been provided by iOS, whereas Android never basically blocks anything to be running and after as in a background service. So that's why sometime for Android there is less efficient memory management, and Android operating system requires more memory to execute the program, and cleaning is not that easy in Android. That's why it sometimes hangs. Nowadays your Android phones comes with many large memory, and that's why there is no lag, but still there is performance difference between these two. Why? Because how it allows different program to be executed. Android never stop any program to run as service in the background and can provide foreground service to any other any application which is there. So but the services has no user interface and they are small in memory use. So this is basic difference between iOS and Android, because it allows the services to be executed at backend. uh, this we have already discussed. Now coming to the process creation. So whenever your program is loaded up, a process would be executed and it will create a pair. The parent process creates a, yes, I agree, Robert. That's why Android system needs more RAM to run, because they never kill any process basically. So iOS manages a better way. So this is how it is basically handled. Anyways, the process, whenever you load your program, a process is created, and a process can create children. Further, uh, further it can create a tree of processes. So one process can create another process, and it can actually create a tree of the processes. uh, for Linux, we usually identify each process by its process ID. I've shown you in POC file. So you saw that each and every process, it has a uh, different directory for each and every process. Now, resource sharing is an option. Now, whenever parent creates a children, the resources can be shared, or children can have their own. Children can ask for their own resources from the operating system. So, what it means that, like, each process would be allocated and given some memory. So, from when a process creates a child process, number one, the process can allocate the memory and other resources from its own quota. Like, one process has some quota of things, it can give that the child out of that particular quota. Other way is the process, whenever a child process is created, it can ask the operating system to allocate the new resources and memory spaces. So that are two ways of doing, but normally it is done like the process allocates the resources and memory from within its own allocated resources list. Because when a process when a parent process is basically terminated, it would terminate all its children. So that's basically happening through that hierarchy. It depends. Now, it's not like every operating system does like the same way, but it depends, mostly do the same way. So in addition to supplying various physical logical resources, a parent process may also pass along initialization data to the child process. We will see shortly like how this would happen. So whenever a fork is called, the fork and operating system can start sharing the same data. So same information would be copied for your fork process. Parent and children can execute concurrently. So they would become independent and they would be running concurrently in the same fashion that are running in basically running two different processes. And then parent wait for children to terminate. So the only difference is parent has to wait for its children to terminate, and once all children are terminated, the parent process can terminate itself by sending the exit command. Now, this is the tree of the processes. So whenever you boot your Linux system, so the first process that runs is system D with process ID 1. Then it creates further child processes. So it forks create a login process, and then it creates SSHD. We remember, like, all of you are doing SSH to your terminal, something like this. How this is happening? Because SSH is already running on your Ubuntu machine. So this was running as a process ID 3028, and it is listening to incoming request for giving for authentication. So here, this is SSH, this is a port number where your process is listening to the request. This B is basically, this is small, this is basically telling the P attribute, the port attribute, then this is user, and then the local host is your host. So this could be the IP address. So IP address could be your EC2 instance, or it's the domain name that could be used here. So this is the username using which you are going to log in into. So login services, one, you open your terminal of virtual machine when you type in OSC, and then this would actually enable the bash terminal, and then further all those programs would start. Whereas through your terminal through SSH, this would be created like this hierarchy. So the one process would actually create other child processes, and the main process, the parent process, would always wait for the child processes to be terminated. So there are different now you can see different processes and their hierarchy, how they're created. So address space, a child can duplicate parent address space, and then the child program has a program loaded into its address space. So how that is done? So fork is the function or the system call that is used to create a process. Then exec, this exec system call is used after fork to replace the process in the memory space. So whenever you basically create a process, and the child process, it can execute this particular system call to load its new content. So you can pass in the address of a new file that you want to load, or you can write a program there, or you can just basically pass in the address of the file which you want to executed by your child process. So let's see on fork. So fork creates a new process. The child is a copy of the parent, but it has different PID. So the process ID is different. Its resource utilization is set to be 0. So fork returns the child PID to parent and 0 to the child. So this is the difference here. Now mind this thing, like your fork would return two different values to two different processes. So whenever fork is called, it will return the PID, child PID to the parent, and 0 to the child itself. So this creates a split between two processes. We're gonna see it. So now, like I said, whenever I take PID equal to fork, when PID calls a fork, so if the PID is less than, now PID is less than 0, it means yeah, fork was not successful. If PID is not equal to 0, it means the PID is there. So it has the fork, the child process has been created, and then the parent would actually say, this would print, I'm parent and my child has PID this. Okay, and what about the child? So else I'm the child, my PID is this. So how this happens? So whenever a fork basically called, let's see, whenever a fork is called, this parent would be copied. The address space would remain the same. So parent has the same, the child has same address space of the parent. Okay, then let's see here at this program. So initiate A with 12, then we fork we create a process, and if it is whatever it is, so it will be running this particular part. So because it will return something, so it will be going inside and it will print 12. Okay, now if PID is not successful, then basically this is if statement. So if this is not successful, or your value is 0, so this is boolean. So if the value is 0, this part of program would not be executed by a child process, because PID for that process would be 0, and this statement would not be true, else what part would be executed by the child. So just, yes. So fork returns a PID basically. And now we look at these two copy, and then we have your parent process is doing something because it returns something, it is true, then it started doing going for a sleep, and then printing something out. Okay, and now this is the state like before both the processes, right before the sleep. So activation record for sleep goes to the stack, and identical but extra activation record for the parent. Now here you could see the stack is as is, and here is basically the activation record for the sleep. So parent is activated, the memory space for parent is activated or modified, whereas child remains the same. So, but we can see here what child process is doing. It is actually adding A3 to the A variable. So you could see the data here has become 15, whereas for the parent process, it remains the same. So what happened after the fork, it splits into two parts based on it creates a replica. The child process creates a replica, and within that replica it performs its own task. So can you answer me based on this? uh, can you answer me on this, like what would be printed at terminal, and who would be printing the value of A at terminal? Quickly, just okay. Child is not printing anything. Only parent would print. Like there would be one printing only. So there would be one printing because this is printing, this is not a printing. If we could have this line here, then it would print like 12 and 15, because the parent process would print and then the child process would print, because now they are two different processes. After this particular part, it creates two processes, one for parent and other for the what I say, the child process. Okay, this would be executed only by parent because PID is not 0 here. Okay, so when PID is 0 for the child process, so this part would not be executed by your child process, only this part would be executed by the child process. Okay, now okay, so let me show one example here. We are running out of time. Okay, so I want to show you. Okay, so this is a program. What I'm doing here is I'm creating fork, fork. This is taken from Geek for Geeks. So fork, 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 and print hello. Now we have to, how many times it would be actually running. So this is a point of understanding. Okay, so this fork would create, sorry, this would create one particular process or child process, C1. Now after this, you could see at this point there would be two splits. One, your parent program is running. Now another, after this, your child process would also start running. So this here, your child process and parent process would fork this second both. So how many would be there? So there would be C2 and C3. Okay, now here, how many processes are till here? It's like second line. So now there are parent process, your this C1, C2, and C3. Now moving toward this fork, this this would be executed by 4 times. So 4, C5, C6, and C7. So four child processes. So in total, how many times your hello would be executed would be equal to the number of processes those are created. So with this, we created 7 child processes with these 3 forks and 1 parent process. So it should actually run for it should actually say it for 8 times. So first is by parent, then 1, 2, 3, 4, 5, 6, 7. So in total 8. So how many processes were created by 3 forks consecutively? 8. So that make it to the power 3. So to the power n is basically number of times, and n here is number of time fork is called. So these many processes would be actually created. Now, can somebody just guess over, like, can somebody guess over how many times this hello would be executed? Just quickly, 1 minute. Any guess? So here the process is basically one parent process and it will create a child process here. So these would be executed by 2 times. Now this would create how many? Like one is created by your child process and other would be created by your parent process. And how many times this would be executed? Now till here we have 4 processes. So P0, C1, C2, C4, 4 times this. So total is 6. Total is 6. Okay, so this is how it is executing, and let me just quickly go over it, and then I remove then I release the poll. So execute is a function which basically load your program into the load child program. If we want to do something different than the parent process, then it loads the program into the main memory. And wait is used by your parent process to wait for your child process to be terminated. It basically returns back us some information which is used by other programs for termination, because time is running short. So I'm just going quickly over it. Now this is what is given on in your book. So we initialize a process ID, then we fork the system, and if PID is less than 0, so fork was not successful. Else, if PID is 0, it means child process has been created. So it means now this is the version of execute. It is basically running this particular command. Now this is loading something. This is saying that this child process is doing something different from the parent. Otherwise, it can keep everything from the parent and just working on it. Now, if your PID is, because fork returns 2 addresses, for the parent, it is PID is positive number. For the child, it is 0 number. So on child process, this would be executing, and on parent process, this would be executing, and where it is executing wait, and it will wait for the child process it to actually uh, terminate. So for termination, we have exit call. We can discuss this in the next lecture. Let me quickly release the poll. Meanwhile, you give answer. The difference between fork and exit is basically your that fork creates a process and execute load the program for the child process into the address space.
I just like to ask for everyone's doing the quiz. Do you know when quiz 3 will be up?
Quiz
Yeah, quiz 3.
quiz 3 is up.
Um, oh, it isn't up on my end.
Oh, I can see, no problem. Let me check it. I'll just do it right now, okay? If it is not.
Oh wait, thanks.
Yeah. Let me just check it if okay, there are few things that I would like to share as The PPTs that I'm discussing, those are not like exact content from your book. I'm following Galvin book. So please refer to your textbook for the quizzes. And yeah, so that's the only thing. And one more thing, I would be putting annotated PPT only because uh, like I got mail from some student, they say that okay, just put one PPT. So for that, in case it is annotated, you can remove the annotation by just going to, if I open this, if you can see my screen. If you can see my screen, you can remove the annotation by going to review. You can go there to review and just hide the ink. So it will hide every annotation. So please do it. I will be just uploading whatever we are discussing and annotated PPT. But if you want that without annotation, you can do it unhide or hide or unhide from here under review button. Is it fine? One or two yes would be fine for me. Am I clear on it? Okay, yeah, thank you so much because it creates multiple location or files. So okay, so for today's process, that when a child process is created, which of the following is a possibility in terms of execution of address space? So this was all of the above. The child process can run concurrently with the parent. Child process has a new program to be loaded into memory. Child process is a duplicate of the parent. So all of above was the right answer. Then degree of multi-programming was basically the answer, that the number of processes running in the memory. So degree of multi-programming is refers to the number of the processes in the memory, and that's why the medium scheduler basically reduces the multi-programming degree because it swaps some of the main memory processes onto the disk, and that's why this basically is uh, is reducing the multi-programming degree.